On to today's webinar's agenda. Firstly, we are going to discuss what is structural ray tracing and why is it important. Then we will move on to the live workflow demonstration, and after the demonstration, we will conclude our webinar. So why structural ray tracing is important? In structurally complex situations such as salt, shale diapers, thrust faults, buried reefs and hills, all these situations affects the quality of seismic data because of seismic signal distortion and noises. To overcome this problem and better understand and interpret our seismic data, we need a tool where we can make this complex structure model cross-section with all the velocity information of the subsurface layers to finally get the ray tracing of these complex structures. Before moving on to the ray tracing, just to give you an idea about our logM packages. So GeoGraphix basically contained two types of logM packages. First one is a logM Advanced Synthetic. logM Advanced Synthetic software is the industry standard for seismic synthetic generation. It provides geoscientists with all the tools necessary to accurately tie well control to seismic data. User can quickly link geological and seismic data and then view the predicted seismic response to the geological concept away from the well. This capability can dramatically improve interpretation, accuracy, and minimize uncertainty when determining the next well location. logM software is integrated with SeisVision 2D, 3D software to enhance the accuracy and confidence of your physical interpretation. Seismic trace data and the synthetic data can be compared in real time with no cumbersome import-export to merge the data and make the final connection. The logM software is sold as a standalone application and includes modules for fluid substitution, cross-section editing, interactive stratigraphic modeling, and advanced synthetics. The second part of logM package is the logM modeling package. The logM modeling package is an add-on to the advanced synthetic package and includes industry's standard stratigraphic modeling and structure modeling. Stratigraphic models are easily generated from the cross-section view and include the formation correlations. Subtle changes can be input to the model and the corresponding seismic response quickly observed in SeisVision. In complex structural areas, the ultimate goal is to determine the geological structure from the observed seismic response. logM modeling software provides the explorationists with the power and flexibility to model a structure and determine the expected seismic response in highly structured areas where steeply dipping reflectors and non-uniform velocity mask the true bed geometry. Structural modeling can be accomplished with either normal incidence or ray tracing. FK migration is also available as an add-on to logM modeling software. The forward models are integrated with the LMKR GeoGraphix applications, enabling the creation of the model directly from a cross-section view. The results can be immediately viewed in SeisVision software for comparison with the trace data, providing a seamless workflow from geological data to model to geophysical data. So let's move on to the today's topic, structural ray tracing using logM struct. So struct is a part of logM modeling suite and is specifically focused on analysis of structurally complex situations such as thrust fault, salt, shale diapers, buried reefs, and hills. The program is used to study the effect of such structurally complexity on seismic data. Struct is a comprehensive forward seismic structure modeling tool that is used to determine the seismic response of complex geological structures in areas where there is little or no well control. It combines an easy-to-use interface for creating complex geological cross-sections and powerful synthetic trace generation tools for producing accurate seismic response. Struct is made up of two programs, the model entry program for creating structure models and the model viewer program for viewing and plotting trace models. So this is the case study which we are going to see in our demonstration. So the structure you are looking here is shared by us with one of our client in UAE, as they are operating in Gulf of Suez area, which has this kind of structural trend. So they wanted to make a structural ray tracing model of these kind of structures, and they were looking for software in the industry which can do this. They have shared this SP paper with us, and we took it as a case study, and we showed them our GeoGraphix logm can do ray tracing, and they were happy to see the results. Idea of using these structural ray trace model is to further correlate this model with the current seismic data and further refine interpretation based on these structural ray trace structure models. So let's move on to our live demonstration. So I will just minimize my presentation, and I will show you the software. So this is the GeoGraphix logm modeling package. As we have seen in the presentation, it contains two different packages. One is the logm advanced synthetics, and the second one is the logm seismic modeling. So today's webinar is going to be based on logm seismic modeling. So I'm going to start my workflow. So first of all, I will open my static graphic modeling module, and I will go to File, New. So you can see a list of the wells here. So I am going to select one of the wells. So for this workflow, at least need one well. So I am going to select a one well 3 times, and I will tell you why I am selecting it 3 times. So as soon as I select well and click OK, it is showing me the new cross-section parameters. So this is the spacing between the wells, and I can see the start and end depth, units, and the depth mode. So I will keep the defaults, and I will click OK. Okay, so the reason why I selected the single well 3 times was to give the extents of my cross-section. So I can see the wells with the curves and the synthetics. Now I will go ahead and I will save this cross-section. I will just give the name for the cross-section. So as soon as I give a name and save it, it will give me a message that cross-section has been saved. So I will click OK, and I will close this model builder window. So now I am going to open the structure model entry program, which is also known as struct. So I will go to File, and I will import the same cross-section which I have just created and saved. So this is the cross-section which I have created. So I will select it, and I will click OK to open this. So as soon as I select it, it's showing me again the wells and the curves which are present in these wells. So I'm selecting sonic and density curves. I will click OK. And now here is asking for the name and the title for the model, and it's also showing me the number of horizontal samples, datum elevation, and the end depth for the cross-section. So I will keep the defaults, and I will click OK. So now I can see my wells, the curves, and the formation tops. I will just switch off the formation tops to clearly see my log curves. And you can see the scale, the depth scale on the left side, and the horizontal scale in feet. So now I will go ahead and I will start picking my surfaces. So for that, I will go to Edit and Input Horizon. So now here you will define the name of the horizon. You can select the line type. So we have different coloring options, the thickness, and the pattern for the lines. So I will keep the default, and I will click OK. And now you can see my cursor has changed to the picking mode. So I will just start picking my surface. So after picking the surface, the next step is to tie your surface with the edges of the cross section. So for that we have the utility that is tie horizon, channel and fault. So I will click on this and it will open a new window for me. So as soon as I open this one, you can see it will show you the dotted line, red color line, to tie it with the cross section edges. So here I think I need to just remove a part of it. Okay, just let me just remove this one and I will pick it again. I will just pick up horizon again. Okay, so then I will again pick up the second horizon. That will be horizon number 3. So this time I am going to remove some part of the horizon to interpret my faults. Okay, so now I am going to interpret my faults in this section. So for that I will go to edit and I will go and edit in input fault. So I will keep the defaults and I will edit interpret fault here, this, and then I will interpret a second fault on the right side. So as soon as you interpret horizon and faults, the next step is again to tie your horizon with the faults and edges of the cross section. So I will select the horizon and again I will go to tie horizon, channel and faults. So again it's showing me a dotted red line to tie it with the end. And again on the right side. Like this. And this one and this one also. Okay. So once you interpret your horizon and faults, the next step is to define the velocity information for all these intervals. For that you will just right click on it and you will give the name of the interval and you will select the pattern, whatever the pattern is, and then you will define the velocity for each of these intervals. So as soon as you give the information, it's ready to apply. So this is how you can provide the lithology information, velocity information and all the details. So now this is the way how you can interpret horizon faults and make your structures. So now I will go to the one which we have seen in the presentations. This one. Now I am going to go ahead and I will show you the similar model which I have created in the struct module. So you can see this model. This is a similar model which we have seen in the presentation. So I will just switch off my well tops to see it more clearly. So you can see each layer is defined with a different color and the different velocity information. So just to see it, I will just right click on each of the interval. So show you, like, this is the name of the interval, this is the pattern, and this is the velocity information for this pattern. Again, I can just right click on this and it's highlighted again in this blue color, and you can see the name and the velocity information for this interval. So once you define your cross section, you define the velocity information, the lithology information, the next step is to go to synthetics and generate your different trace models. So we can generate 5 different type of models: diffraction, normal incidence, image ray, vertical incidence, and short record. So I will first go to diffraction. So as soon as you click, it's asking you to trace generation parameters. So here you can give the name for this model. You can select the units and the wavelet with which you want to make this model. So I will keep the default and I will click on generate trace. So as soon as it's completed, it will be open to view in the model viewer. So I will just go ahead and I will change my scale to aspect ratio not to 1:1, so I can see it more clearly. We have different viewing options in the model viewer. Right now it's in the body fill mode. You can change it to the color trace mode also, so you can clearly see the reflectors. You can change it to the velocity mode. We can change it to the density mode, and we can change it to the acoustic impedance mode also. So this was the diffraction model. So now I will just go back to synthetics and I will generate the normal incidence model now. Again, I will keep the defaults and I will click on generate trace. So as soon as they are finished, they are ready to be viewed in. So this is the normal incidence model. So again, I can change the view options. I can change it to body fill, velocity, and density, and acoustic impedance. So again, I will just go and I will just close this one, and again I will generate this time I will generate image ray model. Again, you can select the parameters and the wavelet. I will keep the defaults and I will click on generate trace. So here I can see my next model. I can change the scale, and again I will move it to the different viewing options. So that is how you can generate different trace models using these 5 options. So once you generate trace model, you can save it to the segway to view or to load it to any seismic interpretation module, or you can plot it directly from here. You can print as a CGM. So now let's wrap up our webinar and move to the conclusion. So integration model is integrated with geological and geophysical data in the project, so the models can be created and evaluated with the data easily. No ASCII transfers or print copies are needed. Flexibility: surfaces can be removed by user control, specifying on-lap thinning or erosional truncation as log interpolation options. Input wells can be easily edited to model different scenarios, such as thinning sands or changes in fluid content. Accuracy: the system provides tools that increase the confidence in the interpretation by viewing the predicted response from the geological model directly with the seismic data. Ease of use: LogM modeling software is easy to use and offers seamless integration to the interpreter, encouraging iterations of modeling to converge on the best possible answer.